There's been a bit of controversy here, but there's been much more controversy about what our next speaker will be talking about in a moment. The last time him and his co-author, David Hockney, were here expounding their theory at the Met, there were picketers outside. You've seen extensive security, barricades. Don't mistake them for anti-Falco demonstrators. It's another event. But I really believe that if there's something that will get me fired at the Met, this is possibly this lecture. I think it's also going to be an extremely entertaining and interesting excursion in physics, archaeology of the Renaissance, and art history. So I hope we can, you will welcome here Charles Falco, the chair of condensed matter physics and a professor of optical sciences at the University of Arizona. And I'll leave you.
So I am the only speaker who is starting the lecture with a fanfare of trumpets, so I hope this lives up to it. Unfortunately, I have about 20% more material than I should have for a lecture of the appropriate length, so I'm going to talk 20% too fast. You can download all of my papers from my website, though, and all the information there. A few quick acknowledgments. I'll talk about David Hockney in a second. David Graves and Richard Schmidt are David's assistants in his London and Los Angeles studios. Martin Kemp is an art historian at Oxford who helped David with some of his early work. Jose Sassian is a colleague of mine in the College of Optical Sciences who ran an early ray tracing calculation. I'm not going to show that today. I'll tell you about the other two in a moment. An outline of what we're going to cover this afternoon is I'm going to give you a general introduction of what this whole topic is about and talk about the technology that was available at the end of the medieval period for projecting images. Then I'm going to talk about optics. I'm going to teach you all the optics you need to know to evaluate the evidence I'm going to show you, and I promise I won't teach you any extra optics. So this is the part of the talk you really do have to pay attention to. And then I'm going to show you selected evidence of various kinds. I honestly could talk for more than 12 hours with the evidence that we've collected at the rate I'm talking today. So I've got to pick and choose different pieces of evidence. Some evidence addresses certain aspects, other evidence different aspects, and I've tried to pick and choose appropriate evidence to show you, and then I'll conclude. David Hockney, for our purposes, since this was is part of the World Science Festival, I assume there might be audiences also of scientists and artists. So a little bit to give you background.
David Hockney, our most celebrated living artist.
He is considered to be one of Britain's greatest contemporary artists.
His originality and skill have ensured his success from the beginning of his career.
The reason why this is relevant, why I want to talk about it is David's eye as an artist was a critical factor in looking and seeing certain evidence in certain paintings that led him to believe optics had been used. And
I admit, for instance, I am interested in pictures. I keep saying this. I'm interested in how you make pictures.
You can go back through David's writings back 30 years, and you can see certain paintings have bothered him. Bothered him in a scientific kind of sense. Any scientist in the audience will tell you that sometimes they've done some experiment, didn't have the technology to collect the data they needed. Many years later, new instruments are developed, have gone back to solve the original problem. It's kept bothering them. And many of these issues that I'm going to talk about today, it's because David has been interested in how paintings are made. Already our technology is letting us down. There we go. The other two acknowledgments. In 2000, Lawrence Weschler wrote in the New Yorker an article about how David Hockney had an idea that certain paintings had optics used. And he really didn't understand at the time what he meant by optics, other than it will distinguish between there's the optical projection of images and the use of those projected images, as I'm going to show you, or there's eyeballing, just how we traditionally think about how artists do paintings. Another story don't have time to go into. I was co-curator of the Art of the Motorcycle at the Guggenheim 10 years ago. My co-curator, my fellow co-curator, Alton Guilfoyle, called me when this article appeared, said, I'm in Tucson, He knows I'm interested in art, knows I'm interested in optics, and said, Falco, I don't care what you're doing, drop it, go buy the New Yorker, read that article, and call me back. Typical New Yorker didn't realize that the New Yorker doesn't get delivered in Tucson, Arizona, the same day. So the stories paused for 2 days till the New Yorker showed up. Then Alton put me in contact with Ren Weschler, who put me in contact with David Hockney, and this became the most intensive scientific collaboration of my entire career. In the first 6 months, David and I exchanged a ream of faxes, 500 pages of faxes. And we weren't Xeroxing books and sending copies of articles from books. These were handwritten or typed faxes. It was a very heady time. And such that the European Science Foundation has organized a symposium on what I'm going to tell you today is the Hockney-Falco thesis. It's what is the scientific evidence that shows that artists early in the Renaissance were using optics. And the important point about this is that every painting I'm going to show you today is from the Metropolitan Museum, the Louvre, the Hermitage, from major museums that are visited by an estimate, if you believe their attendance figures, which there's reasons actually not to believe. But if you believe their attendance figures, 25 million people a year see all the artworks I'm going to show you, and 25 million people a year after year, didn't see what I'm going to show you that we extract from these paintings. And as Marco pointed out, this is inflames passions. This is a press release 2004. This group picketed the Met and marched with petitions denouncing us for having defamed the old masters. Now, there are many things you could picket for, and there are reasonable things to picket for. If at the end I've convinced you that Jan van Eyck used a lens, that's not, well, you have to be pretty passionate to picket against that, to denounce people for that. Most scholars would agree that optical instruments first appeared late in the Renaissance with the invention of the telescope by Galileo. Now, if you're an expert, you know, well, Galileo didn't invent the telescope. People say he kind of stole the idea from a Dutchman at the time, but the year 1600 or 1598, nobody disagrees with that. If you want to project an image, you need a lens. Mirrors only reflect images. You just go to the restroom, convince yourself of that. Van Eyck, Bellini, these were Renaissance masters that work by sheer genius alone. If what I'm going to show you tonight, this afternoon, is true, all of these statements are false. They're not false on a technicality. They're fundamentally false. So the evidence I'm going to show you actually goes to the foundations of a liberal arts education. If we look in humans' attempts to represent the human form in 2 dimensions, well, 1900 BC, we learned 2 things from this. One is that they couldn't paint very realistically 4,000 years ago, and they also, though, they can paint better than I can. We come forward in time, much more elaborate, but still a flat, 2-dimensional look to it. But we come to Van Eyck. If this man walked out through that door right now, everyone in this auditorium would instantly recognize them. How did Van Eyck capture such realism? And it turns out there's a clue, a very strong clue, in the painting itself. Everything I'm going to show you today, every aspect of optics that I'm going to show you that's used by artists, could have been done with this pair of spectacles, with a pair of reading glasses, like many of the people in this audience are wearing. You can project images, beautiful images, and I'm going to show you with a pair of reading glasses. I'm also going to show you that there's really strong circumstantial evidence that early on that they didn't use reading glasses, they used concave mirrors. But one thing, we're going to say Van Eyck used optics. He had the optics in his painting, so clearly it existed at the time. So my lab is on the 10th floor of a building. We're going to be looking down. I'm going to have my assistant turn that pair of reading glasses, and you're going to see the projected image. And she'll stop at a certain point. We come back, we see the projected image. And we stop here, we see the projected image, the sky is above, the directly reflected image from just the front surface of the glasses. The sky is above, the ground is below. Projected images are upside down. Every projected image is upside down. The ground is above, the sky is below. But you can see we can project images with spectacles. attempts to represent geometrical objects in perspective. We come to here, but it doesn't even take very careful look to see that although that's a hexagon, and it's sort of tried to be in perspective, if we fit a perfect perspective-corrected hexagon to it, it doesn't fit. The Jan van Eyck chandelier. Well, let me magnify this. That chandelier, I want to remind you, that screen is, 15 feet across. That chandelier, if I went to the National Gallery and the guards let me do this, I can cover that entire chandelier with my cupped hand. So I've taken something that's this big, blown it up to 15 feet across, and it maintains its incredible fidelity. How did Van Eyck do that? And I'm going to tell you how he did it. Let's see if it's in perfect perspective. So what we'll do is we'll fit a perfect, idealized, computer-generated chandelier to it and see how well it fits. Well, at first glance, it fits extremely well. If you look a little more carefully, you see, well, it's off by a little bit here, by a couple of millimeters. But as I'm going to show you, that is going to be evidence that optics was used. Because there are ways to generate by just the laws of perspective, which had not been developed then, to do something in perfect perspective. But there's no way you can project a handmade 15th century chandelier. It can't have the fidelity of a perfect object. And we're going to talk about that. Well, the question is, did they have the technology at the time? I've already shown you that they had the spectacles at the time. I'm going to argue that they used concave mirrors early on. If we look, here's this catalog of medieval and Renaissance books, textbooks on optics. There were 65 treatises on optics. It's a critical period, actually. There's an Arab scientist I'll mention in a little bit, Ibn al-Haytham, 1000, up to the time of Van Eyck. One new textbook in geometrical optics is written every 7 years. There aren't that many new textbooks in optics written today. So if you would have asked me, 10 years ago, what was going on in medieval times, I would have, explained to you the Cro-Magnons were fighting the dinosaurs. Really, nothing's going on. It turns out it was a period of intense intellectual activity. One problem was that the people back then were not very intelligent. They couldn't write in English. But so some of these texts, though, have been translated, not very many, been translated into modern European languages, and they describe exactly how to make a concave mirror by polishing out of metal in the grinding paste it takes to do that. And I've made these mirrors. Well, for you New Yorkers, that's called a cactus. So what I'm going to do is with my handmade mirror that I made myself out of, well, in this case with aluminum, but I like brass better now, that I made in 1 hour, I made a mirror that I can project this backyard scene, the individual, on some projectors it's easier to see on others, the wrought iron fence. We can see the wrought iron fence here. That gives me an angular resolution. I can tell you how good my mirror is. My mirror is approximately 3 times better than Van Eyck would have needed to use for any of his paintings. For those of you who are scientists, though, it's 2,000 times worse than the Hubble Space Telescope. So where we think as scientists it takes really great optics to do something, to polish something, to project an image. No, in fact, it doesn't. And to see how bad you can do, I bought from a wholesale restaurant supply company in Tucson a stamped stainless steel, made in Korea, spot welded, with holes in it, ladle. And what I'm going to do is I'm going to project the scene of outside my lab from the 10th floor, and I've got a photograph of what the lab is. You can't simultaneously see the projected scene and the direct scene, so you just have to compare the two, and we'll see. I mean, a scientist would say you could never project an image with that unless you tried it. Now, it's not the world's greatest image, but it shows you how awful your optics can be. That image is certainly good enough for a clever person to have developed the laws of geometrical perspective. For Brunelleschi, just seeing that scene alone. One of the good things about being involved with somebody as famous as David Hockney is people have contacted me with useful information. Some of the bad things are people picket, call at 3 a.m. to denounce me. This strange stuff goes on. You guys are interested in art, or sometimes you're a little too passionate. This was one of the good ones. He emailed me and said, "You're easier to find than Hockney. Are you aware of the discussion of mirrors in The Romance of the Rose?" Well, I confess I'd never heard of The Romance of the Rose. But it turns out the Barnes & Noble bookstore in Tucson, Arizona had 2 copies on the shelf. Now, if you're familiar with publishing world, you know that books go out of print like 5 minutes after they're published, just because of the tax laws. The fact that there are 2 copies of this book written 600 years ago on the shelf tells you it's widely used today in the humanities. And what the translator says, it was the most widely read work of the French language. And unlike me, presumably Jan van Eyck, who worked in the court of Burgundy, spoke French. There are 4 pages that discuss the properties of mirrors. You're not able to read that, but if I magnify certain sections, it describes El-Azane, wrote about the properties of mirrors. That's Ibn al-Haytham, whose seminal textbook, 7-volume textbook, in fact, describes our modern understanding of vision and perception and optics today. His book was translated into Latin at this time, and it was widely influential, including places like Chaucer's Canterbury Tales. El-Azane is discussed in there. And the poet says that I'm not going to take the trouble to clarify the shapes of mirrors, how rays are reflected, or describe their angles. I'm not an expert in French epic poetry of the medieval period, but this strikes me as awfully technical language for a French epic poem. If we magnify one of the pages, I'll skip over some of this in the interest of getting us done on time today. Certain mirrors make phantoms appear quite alive outside the mirror, either in water or in air. It's not like water and air rhyme in French. That's not why he used those words. Water and air were of great interest to the philosophers at the time. A solid, light doesn't go through. Air, light goes forever. Water is sort of funny. It's in between. In some ways, it has the properties of a transparent substance. Other times, it has properties of an opaque substance. Before we'd ever heard of The Romance of the Rose, the BBC filmed us, and one of the things in the film is David Hockney is describing this projected image of a cabbage. It's upside down. We already know that all projected images are upside down. I want you to compare how a 21st century artist describes this scene with how it's described in The Romance of the Rose.
And I realized this is a color movie. It moves. I mean, there it is. It's spinning. It's quite beautiful. Of course, it's upside down. The strings coming from the bottom. And I then realized, my God, this is a movie in color. They must have seen it 600 years ago.
Well, he was wrong. They saw it 700 years ago. So up to this point, I've shown you that they had the technology to make the optics necessary to project images. They understood how to project images. It remains for me, though, to convince you that artists actually did project images and make use of the projected images in their artwork. And so for this, I have to teach you optics. And it's dangerous. It's comfortable chairs, dark room. Pay attention, though. This is the part where you really have to know what I'm going to show you in order to evaluate the evidence. Well, one thing we've all been taught is that parallel lines all lead to a vanishing point. No one bothers telling you, though, that objects that are right along the same railroad tracks but slightly deviating from being along the same lines, they're deviations from perfection. So if we come across a painting like this and we draw, this is too good to be true. There's no way, I've been to Italy, no way do the Italians construct the facade of that building exactly parallel to the facade of this building. You know that. So we can be reasonably sure, because of the degree of perfection, that this painting, made after the laws of perspective have been developed, that this painting was done not with optics, but was been done with the laws of perspective. Widely used textbook in art history. Our camera, in this case, is above the object. Parallel lines lead to vanishing points, and the vanishing points are on a horizon line that are at the height of our camera. I'm going to show you a photograph that I made where the camera's below. It's of a chandelier, so we should have vanishing lines down here. It doesn't look like we were taught. I can guarantee you that this is an optics-based image. I took that photograph myself with my own digital camera. Yet it doesn't agree with what we were taught it should do. And the reason is that slight deviations of where those arms are, and those arms are presumably in good enough position to convince you to pay several $100s to buy that chandelier, that slight deviations that are not noticed by the eye lead to just this total incoherence. Science has to be reproducible. That's a different chandelier in a different Home Depot, and it both agree here. So deviations from what we've been taught of a geometrical perspective are going to be one of our clues of whether optics were used. Here's David Hockney visiting my lab. If you didn't know how tall David Hockney was, and you probably don't, you could look up in an almanac to make an estimate, what's the average height of a European male, and that's 1.75 meters. There's Ren Weschler also visiting the same day. That tells us the horizontal distance across the scene at the depth into the scene at which David Hockney is standing. Well, everyone knows a molecular beam epitaxy console is 2 meters long, so we don't have to look that up. And that tells us that a 22 millimeter focal length lens was used to take this photograph. My technician used a 24 millimeter focal length lens. Now, that's not magic. That's geometrical optics. That within the uncertainty of just our estimates, we can, if we can find, if Jan van Eyck painted a molecular beam epitaxy machine, we're in great shape. We can determine the focal length of the lens that he used. And we're going to make use of this. Here's Arnold Schwarzenegger. Even if you get nothing else out of this lecture, I'm going to affect the way you look at movies in the future. Arnold looks back into the scene. What changed? Well, clearly, the cameraman focused further in, but that's not all that changed. If I bring Arnold's head back, there are two equations of geometrical optics. There's the trailer. We can know how big his image was originally projected because it was shot in a particular format we can look up. I know how tall on the negative that film was. We can estimate how tall Arnold's head really is in real life. The magnification is 0.06. I remind you, go look at any Renaissance portrait out here. The magnifications of the Renaissance portraits aren't 0.06, they're 0.6. They're more like half life size or close to life size. So they're 10 times larger magnification. The effect is that I'm going to show you, which is real here, is even magnified more in the paintings. The length of the trailer from those kind of fuzzy out of focus images, we have Arnold look halfway back. It seems like the trailer shrunk. He looks all the way back, it shrinks some more. Well, it doesn't shrink. It was an 8% change in a movie that all of you saw, and you never noticed that change. You'll never not be able to notice these changes in the future. That one of the consequences of refocusing further into a scene reduces the magnification of the image. We're going to make use of that. Again, for you guys in New York, that's a mountain. So we can...
If I let you know where I'm going.
We come in on Tom here. The mountains were a little bit out of focus before. Now they're totally out of focus. Again, we do the same kind of estimate. I'm going to go through this very quickly. Different format, different size. My estimate gives me about the same size for this. But when we come in, we've increased the magnification by a factor of 3, but we've decreased the depth of field of the scene by miles. So another thing, increasing the magnification decreases the depth of field. And the effect is much larger when the magnification gets even larger. And we have equations that we're going to throw at this and calculate this quantitatively. Something I want to remind you of, that we're all too familiar with photographs. It's distorted our way of understanding. I'm going to have to kind of remind you of things that you take for granted that are, in fact, weren't taken for granted before the first projected image. Human vision, we take in pretty close to 180 degrees, not with high resolution. Like right now, I'm kind of looking down the hallway, but I can see the exit sign, I can see that exit sign out of focus. So I'm seeing a huge angle. There is no camera lens, single camera lens, that'll take in that kind of angle. That photograph is taken with the widest focal length lens that is really available for a single lens reflex camera. Parallel lines remain parallel. But when I look this direction and I look that direction, I'm looking in different places. The magnifications change of the scene. And this is how the eye constructs a scene. Before images were projected, here's a painting before images are projected. Looks like that scene. I'm just offering this as something for you to pay attention to when you're looking at the paintings in the Met. So here's how we're proposing that optics was used. Here's somebody dressed up to look like Cardinal Albergati in a Van Eyck painting. There's David Hockney. The door is open so we can see inside. His image is projected and reflected upside down by that concave shaving mirror in living color. It's a movie. The artist then takes the few features he needs to know to continue painting the portrait. And a good artist may only need to capture the positions of the eyes, positions of the nostrils. Doesn't have to trace the whole image. But it's an optics-based image at this point, takes it down, and continues working from life. Fills in the rest. But the optics is already built into it at this point. And at this point, if you decide, well, I want to make this into a painting, well, you add the color. So I'm going to show you a 30-second clip of David doing this. Watch, the guy will blink. It's a movie in color. And David's actually tracing more just for the benefit of the camera than he needs to, far more than he needs to do these optics-based portraits. He's painted 4 portraits of me. I've watched him do this. He doesn't need that much information. Then takes it down, works from life. So at this point, this is an optics-based image in which there are non-optics components built in. The guy was sitting outside. Well, he can put him outside. He could have been painted in Iowa, but that doesn't mean that the artist doesn't have the artistic license to create a totally, out of his own imagination, scene and put him in the sea. Optics-based, non-optics-based. Or he can put him inside. Or he can put him with his friends. These are collages that are evidence. All the evidence I'm going to show you is some features of some paintings were created with the aid of optics. Now, that's not a weak statement. That's a hugely strong statement about the use of optics, but also that's a limitation on it, because you're going to have to know what features to look for to know where the artist used optics. It also does not take away from the creativity. In the Arnolfini marriage, if you remember, there's a husband and a wife. The woman's in green. The husband's on this side. The artist created that composition himself. He may have decided the woman wore a purple dress today. I don't like purple. I'm going to put it in green. He has all sorts of choices that are made. Optics helps him with some features. But it doesn't create all this. So where would optics help with this painting? Well, there's a little dog in this painting. If we magnify the dog, we can identify its breed. It's a Bichon. In fact, I have a colleague who raises Bichons, and he assures me that if you have a camera and you have it set any slower than a 500th of a second, the dog's a blur. So we learn one of two things of this. Either Van Eyck convinced the Arnolfinis to let him kill their dog and stuff it so he could project the image, or Van Eyck had the skills to create a Bichon with his pure artistic skills, if we say alone, his unaided by optics skills alone. So he had the skills. This tells me that Van Eyck has the skills, if you would say, to not have to use optics, if you want to put it that way. But, as I will show you, whether or not he had to use optics, he did use optics. Those are logically separate propositions. The shoes totally could have been Van Eyck's imagination, but where optics would have helped is with this incredible chandelier that's the size of my palm. But even though Van Eyck might have seen this projected upside down, optics don't make marks. He can do whatever he wants with that projected image. He can copy the features he wants, he can ignore the features he doesn't want, and he could have, and he did, create this. They're not photographs. They're more complicated than that. So if we look at this famous artwork, if we want to analyze this work of art to decide was optics used, we better analyze features like this. If you blindly go in and don't understand, and you analyze this feature, you might incorrectly conclude that optics was not used in this composite painting. We need to look for the right things to look for. So if we take this Arnolfini marriage, one of the signatures of the use of optics is, did he use optics to paint that mirror? If Van Eyck's lens was above or below that mirror wouldn't have been round. It would have been oval. So if he used optics, the lens had to be at roughly that position. If we magnify that, let's try that again. So if he used a lens, it's got to be somewhere around there, like here.
Is the man in blue Van Eyck, and the curtain behind him his camera obscura, with the bright object his concave mirror?
Well, if that camera obscura, the one that was actually in the film that I made, was actually made by my daughter, who's in the audience right now, who is when she was in architecture school, she's now a New York architect, she made that camera obscura, which is actually more widely traveled than many of you. Its next good trip is to Saudi Arabia, where I use this to demonstrate various things. That's what a camera obscura looks like. It's a piece of cloth. So people who have been misled, who haven't understood, who are looking for some object, a thing that looks like a camera, are looking for the wrong thing. You need to be looking for a curtain, which we know exists, and a concave mirror, which we know exists. So now with that as background, I'm going to show you very quickly evidence in two paintings. This Lorenzo Lotto and a Robert Kempan that's here at the Metropolitan Museum, so you can look at this yourself. When I first visited David, he has organized on a wall that's the length of a tennis court in his studio in Los Angeles, color photocopies of all the paintings that look to him worth consideration. And he organized them like a scientist would organize things. Paintings from Northern Europe on the upper wall, Southern Europe on the lower wall, chronologically organized. This painting in particular caught my eye, and kind of refer to this to as our Rosetta Zone. One feature that will be more apparent when I magnify it is that central octagonal pattern goes out of focus. And I want you to remember there's a woman in the painting because she's going to be our molecular beam epitaxy machine. She's going to be our ruler. So if I magnify that center section, that goes out of focus. Well, it seems reasonable. Why not? If you've never seen a projected image, you've never seen this before. The human eye does not simultaneously see part of a scene in focus, part of a scene out of focus. Now, the reason why I say that this, I'm emphasizing this, I mean, that looks like a perfectly reasonable photograph. That's not how you would have seen this. You would have looked at the boy's wine bottle, you would have looked back at the car, and your eye would have refocused, and you would have constructed a mental image of the scene that was totally in focus. So the fact that that octagonal pattern goes out of focus is very strong circumstantial evidence that that painter had seen a projected image 75 years before Galileo. If we look at vanishing lines, there's two sets of vanishing lines. And I'll show you in a second there's a third set. If I put it back into the painting, it goes out of focus, I know, somewhere in here. If we look elsewhere, the same depth into the scene where the carpet goes out of focus, we see one set of vanishing lines, another set, and they differ by 3 degrees, and I won't talk about these other features in a second. Let's reproduce this. Every feature I'm going to show you, every bit of evidence, we've reproduced photographically. And I'm only show you this one example. If I take a picture of this, this particular scene, and I focus at the front of this carpet, and I paste together, this is only the bottom half of my photograph. And now what I do is I change my mind. I refocus to this point, and now I'm going to, with Photoshop, I've already painted this, I'm going to paint the top half of the scene after refocusing. And it looks fine, except if you look at it more carefully, you see that the ruler is not straight. It's kinked, and it's kinked by 3 degrees. Just like this. Another bit of evidence. Oops, sorry. Flip through this quickly. A mistake of it. So let's try to fit an octagonal pattern to this. If I take this octagonal pattern, correct for perspective, take away the ruler, have it in color, it's all done to scale, and if I put this on the painting, well, your first reaction should be, it doesn't fit at all. What are you trying to tell me? Optics is used. It doesn't fit at all. But this is not what Lorenzo Lotto would have seen, because this is very high magnification, you would have seen something like this. This is several depths of field into the scene. Make use of it. You're a clever artist. You want to capture this very real. You make the markings here where it's in focus, how it's too far out of focus, then you refocus. As we've already seen, counterintuitively, if I focus on the woman in the front row and I change my mind when I focus on the exit sign, I have to pull the lens toward me. That reduces the magnification. And it reduces by a quantifiable amount that I can calculate. We fill this in, do it again, we fill that in, and we have the entire painting. If I had a ruler, I could make this quantitative. I have the woman. The distance across her shoulders in the painting is 10 inches. The distance across a real woman's shoulders is 18 inches. I know this because I have a wife and 2 daughters. And in the land of the dataless, the man with 2 data points is king. So I've got the data points. I know the magnification of the painting, it's 0.56. That tells me how far apart these triangles are. And instead of this thing going out of focus 5 to 9 repeat distances in, tells me in real units of centimeters, and I can calculate things from this now. So I have these 2 equations of geometrical optics. I have a magnification, the depth of field that I've just measured. So I end up with 6 equations and 7 unknowns. Ooh, what does that mean?
This is it. That moment they told us about in high school where one day algebra would save our lives.
6 equations, 7 unknowns. If I make one assumption, everything else follows. And what I'm going to do is I'm going to assume that I'm roughly 4 feet from the carpet and I've got error bars on it, and I won't go into all that. Everything else follows from this. I have no control over what goes on. Geometrical optics dictates that if Lorenzo Lato used a lens, there have to be 3 regions with 3 different sets of magnifications. And let's see how well it fits. If I look at the distance from that kink across, after refocusing, that distance decreased. And it decreased by 13.1%. Algebra tells me it should have decreased by 12.6%. It agrees to a 0.5% accuracy. Here, different magnification change, again it agrees to a 0.5% accuracy. So did Lorenzo Lato use a lens? Of course he did. There's no other way. We're not saying that optics is the only way to get perspective right. We're saying optics is the only way to get perspective wrong in exactly the way these artists got perspective wrong. And I'm going to just skip over this. There's other ways of getting perspective right. Let me just skip past this. So, summary of evidence, and again, I encourage you to go to my webpage and download all of this. The evidence that this Lorenzo Lato painting, 75 years before before Galileo, overwhelming evidence. I'm going to show one other example, and I'm going to skip the rest because it get done. This is a painting that's in the Metropolitan Museum. There are actually 2 ways to refocus. Here, we had the problem that it was fuzzy in the back. The octagonal pattern got fuzzy in the back, so the way we solved that problem was we refocused further into the scene, which reduced the magnification. That was a Lorenzo Lato painting. There's another way to solve this problem. Just drag the scene closer to you. And this is what Robert Campin did. In this case, the magnification remains unchanged. This is in the cloisters, so take a train uptown, and you'll go to it. I'm going to show you I'm not going to show you this evidence for lack of time. I'm going to show you the evidence in the back of the chair. This complex lattice work, I'll make a lattice work. I'll correct it for perspective and see how well it fits. Well, it doesn't fit at all. I mean, no matter where I try to fit it, it doesn't fit at all. But we remember about optics now. Instead of trying to fit everything all together, we've got depth of field considerations. I'll try to fit just the front. Starts getting bad. Let me refocus my lens. Gets bad. I refocus my lens again. Everything fits to an accuracy of about 1/8 of an inch. No way would a handmade wooden chair made in France be made to an accuracy any better than that. So if it had fit perfectly, we'd have other reasons we might suspect it doesn't fit perfectly. And there's lots of kinks and stuff that we're just going to skip over for lack of time. where we get quantitative agreement. And the thing is, you can see the effects I'm showing you with your own eye. If you walk up to that painting and you look at it at a grazing angle, you can see where that blue line, it kinks into the green line, it kinks into the red line. Infrared reflectogram gives us preferential sensitivity to the underdrawing. There's the underdrawing. There's a qualitative piece of work. Let me magnify it more. One more time, I'll magnify it. There's his headband. Look how Campan made that line. Very sure line. Doesn't look like that at all. There's a line. Looks like this. There's a nice sure line. So from actually Hockney's book, we discovered all of this much later. Warhol projected. If you project an object and you've got the difference between light and shadow, it's just really easy just to trace along it. If you are doing this by eyeballing, you do this. So it's qualitative evidence that goes along with everything else. And the size and the magnification of the lens that we calculate for Campan is comparable to what we have for Lotto. And again, if we just look at this little bit, the evidence that we extract from this painting here in New York is a whole variety of things. And so now I'm going to skip ahead after this runs through. So all of this evidence that's in here, download from my webpage. I'll tell you how to get to the webpage at the end. Ask me the question at the end, I'll tell you how to get to the webpage. A good way to remember it. So I'm going to have to skip because of lack of time. Sorry about that. I'm going to skip ahead to near the end, which is, there's all sorts of wonderful things here that you're missing. So another question, I'll answer the question you should ask. If optics was first started to be used around 1425, when did the artists stop using optics? I'm going to show you a visual history of optics-based paintings. All of these paintings, and many more that I'm not going to show you in this movie, have elements within them that are based on optical projections. But I'm going to cover the 600-year period in 18 seconds. So if you blink, you're going to miss 100 years of art history. So don't blink. Here we go. Every one of these paintings has elements that are based on optics. And they're the iconic paintings of European art from the last 600 years. So the answer to the question of when did they stop using optics, they never stopped using optics. They used it continuously from the time they were first used for the features where optics were helpful. So to summarize, overwhelming scientific evidence that optics were used in a number of paintings. They're not photographs. This does not in any way diminish the artist's skill. If you thought Van Eyck was a genius, you seriously underestimated the man. That these are hard things to use, but the optics was helpful where it was used. And it does fundamentally affect our understanding of the evolution of the art of the past 600 years. It's not that this sudden transformation to realism was not noticed. It was noticed, and it was puzzling. Now we can tell you why it was done.
Here's what's so revolutionary about what you're saying. You're saying the history of art, the history of the Renaissance, is the history of optics.
I am saying
I know that, and you're blowing everything up. You're blowing everything that all of us who took art appreciation studied, all the art historians have written, and you're saying you're all wrong. It's all about optics.
So if you say things like this, you do get pickets. So thank you.